Okay, so I'm supposed to solve 5.2 number 5. Y double prime plus 2y prime plus 10y is 0, which is what kind of beast? Second order.
Homogeneous.
Constant coefficient. Homogeneous.
Differential equation.
Linear. Differential equation. Okay, so to recap. Second order, linear, constant coefficient. What else did I have? Homogeneous?
Differential equation.
Differential equation. Cool. Which is good for me or bad for me?
Good, because that's the only thing we can solve.
Yeah, that's good, because that's the only one I know how to solve right now. Later we'll get to adding a non in front of this hom part some of the time. Right, so on this one I at least have a hope. So what do?
Well, I started by making it r squared plus 2r plus 10 equals 0.
Badass. So that was really thinking like, okay, let y be e to the rx, right, or rt or whatever,
Yeah.
and then divide by e to the rx, right?
Now, would you do that for every single one of these, or does that differ by the problem? Like,
Oh,
could
you mean
just
would
take-
I just jump to this
Yeah,
every
could
time?
you take any of them and just jump to r squared plus 2r plus 10 on any of these?
Yeah, absolutely.
Okay.
The reason that I might suggest that you actually think about making this substitution is I have noticed over the years that students have a tendency to do this,
Okay.
right? They have a tendency to slap an R anywhere they see a Y, and it's you need to slap an R anywhere there's a derivative. Right, so there's two derivatives here, so I got two R's. There's one derivative here, so I got one R. There's no derivatives here, so I have no R's. But that's just like these problems get a lot weirder if you screw that up at the beginning. Okay, so if I'm here, what do I do now?
Now, I broke that down into r plus 4 times r minus 2 plus 12. I'm not 100% on the methodology, but I was just kind of trying to mimic the examples.
Like this or something?
Yeah, I'm not sure if that's right. Because it would turn into r squared plus 2r plus, I guess, negative 2. And then, or maybe not, maybe I did that wrong. Looking at it, I think I did.
So I can get, let me maybe try a suggestion. I don't care how you solve this, but you need to solve this. So you have 3 techniques to solve quadratic equations. Okay? The 3 techniques are as follows. Don't add new ones. Do the quadratic formula. Complete the square. Or factor and zero product rule.
So guess and check.
Do not guess and check. Do math. Yeah, you could also guess and check. It just makes me look down on you.
But it gets done faster sometimes.
No, not this one.
Oh yeah, not this.
I love how you're like, I'm an advocate for guess and check. Oh yeah, don't do that here. Okay, so yes, you may guess and check as long as you are wise. If you fail to be wise, like if you fail your wisdom check, don't do guess and checking, okay? So I might look at this and,
Quadratic, because it always works.
oh, F that. You guys are clever. Why is this a good idea?
Because 9 is like, yeah, 9 is 9 squared.
Because that's an r plus 1 squared. Plus
That
a
grabs r
square.
plus 1 squared.
That's kind of a problem,
Yeah, so if this was Algebra 2 land, I'd be like, yep, no R's.
Oh, but we can use others than that, yeah.
Yeah, but you guys know how to use Euler's at least a little bit, right? So this step here was complete the square, just in case we've forgotten. But I don't care what you use to do this. You're going to have a hard time factoring and zippering on this one. Right? But you could certainly run the quadratic formula on it. That would be totally fine. I saw a square that needed completing, so I completed it. So hit both sides with the square root. So you get r plus 1 is plus or minus square root of -9, gives you 3i. Okay, so you got r is -1 plus or minus 3i's. Hey, yeah, this is actually a springy spring. Like, this is the spring I think about. So if I take this, and what should I be doing with this?
Plug it back to your y equals e to the rx.
Yeah, I should really be thinking this at both sides of that. So now I've got, my solution looks like y is e to the -1 plus 3i times x. I just picked one.
Oh, you just pick one?
Yeah, just pick one.
Oh, okay.
So you just pick one, and then you break this out. So y is e to the -x times e to the 3ix. Maybe let me rewrite that as I times 3x. Cool. So then let me rewrite that as e to the -x times,
Sine of 3x. That's where we hit Euler's, right?
yeah, this is where you hit Euler's. So you do cosine of 3x plus I sine of 3x. And so then you split this into its two pieces. So that's e to the -x cosine 3x plus I times e to the -x sine of 3x. And then after you've done a million of these, or 4, you can just say, okay, this first bit, the real part of this, is going to be my y1. And this bit, the imaginary part, is going to be my y2.
And you leave out the I when you do that?
Yeah, and leave out the I when you do that. What you're doing is you're getting two linearly independent solutions, right? Like, for me to say that I have solved this, I need a fundamental solution set, right? I need two linearly independent functions that satisfy the differential equation. So here I have one solution that points in the real direction and one solution pointed in the complex direction. The real direction and the complex direction are linearly independent, so I can just pull those separately. And I'll just let the constants adjust.
So in the above step then, we had -1 plus 3i, you could just do a -1 minus 3i, and it wouldn't screw you up here?
Yep, because I'm going to pitch that plus or minus sign anyway along with the I.
Okay.
If you put so if you have a -3x, right, you're going to have a -3x in each of these. Cosine's even, so you'll get the same thing anyway. Sine is odd, so you take a minus sign out, but you don't really care what the constant is anyway because you're tossing the I anyhow. Right, and I and minus I are both perpendicular to the real axis anyway. It doesn't make any difference.
When they had us set this up, we did C1 plus C2.
Yeah, so my ultimate solution here should be y is C1 times y1. So I got C1 e to the -x cosine 3x plus C2 e to the -x sine 3.
And my question was, when we solve this, they always give us initial conditions, and C2 is never imaginary. Is that because the initial condition was never given an imaginary starting?
Yep.
Okay.
Yeah, if I gave you an imaginary starting condition, then yeah, you could find C1 and C2 as imaginary numbers.
Okay.
But because we're working in real spring land, right, we expect to get real differential equations out. Or, sorry, real solutions to our differential equation. You guys cool with that? If you want a way more detailed run out of why you can drop the constants, you can take both of these with arbitrary constants, rewrite with Euler's, and demonstrate to yourself that the real part will be this, and the imaginary part will be a very similar thing. You really can run through that, prove to
The
yourself.
imaginary is always attached to the sign.
If you,
Will it ever be attached to the cosine part or no?
yeah, it won't, it'll be always attached to the sign. Yeah, it'll always be on the sign. And you can kind of convince yourself that arbitrary choices of constants will be enough here. Cool? So, Taylor,
Yeah.
where did I lose you?
Uh,
Or where did you lose yourself?
I was able to pretty much figure out all these, if it was neat, you know, just like the first one, r plus 6 times r minus 1 equals 0, I could get those just by mimicking what the other ones look like. But whenever you get that equal to something that isn't 0, I didn't really know what to do, so.
Oh, I see. So if you get to the point where you have, so maybe let me line up the cases. Maybe that'll help.